is to answer a question that was famously posed by Feynman in 1957. And how does this work? Okay. Which is what is the gravitational field generated by a superposition? In the talk, he came up with a weird contraption to put an object large enough to generate an appreciable gravitational field in a superposition, and he asked, okay, what is the gravitational field sourced by this state? And he went on to argue, if you don't believe that it is the superposition of two amplitudes, one of the bulbing up and one of the bulbing down, then you end up having some problems. But fast forward 50 or 60 years, this original, this first idea has kind of been reframed into a test of the nature of gravity, whether it is quantum or not. And the idea is the following: assume that you, this is one of the images taken from the seminal papers in 2017. Assume that you have two systems which are large enough to generate an appreciable gravitational field, and imagine you can put them in superpositions in a then if any entanglement is generated in this interaction, and you're able to detect it in some way, then you can claim that the mediator of the interaction must have been non-classical. It doesn't tell you many information about the nature of like the specifics of the interaction, but it couldn't have been a classical interaction. In quantum information terms, you assume that what it means to be classical is to be an LHC channel, to determine an LHC channel, which by construction entangled systems. And what we realized in these papers in 2017 is that if you use some mesoscopic masses and you displace over hundreds of micrometers, you only need a few seconds of coherence, of maintaining this coherence, to see some entangling phase, which is much less than the scales which are usually required for experiments on the interplay between quantum physics and gravity, which usually require much higher, which usually have much higher requirements. Now, while these experiments are nice in the sense that they bring the possibility to test the interplay of quantum theory and gravity to, let's say, feasible tabletop experiments, they're still extremely challenging to actually perform. And the reason is that creating and maintaining the coherence of large mass superpositions is extremely hard. Like ever since the beginning of quantum mechanics, people have been putting larger and larger objects into superpositions, but there is a drastic scaling with mass. I think the largest, you can put neutrons in superposition over half-meter scales, but as soon as you go to like molecules, like big molecules, you drop down to nanometers. So displacing over hundreds of micrometers becomes an extremely difficult challenge because of the presence of environments, essentially, which induce the coherence. And so the question that we pose ourselves is, okay, in this respect, is there anything left to do other than maybe finding better systems or defining better geometry? So improving the setup until it reaches experimental feasibility, or can you try to find another way to tackle the same problem? And what we thought is, well, the logic underlying these experiments is that entanglement generation is sufficient evidence for non-classicality of the mediator of the interaction. This, in fact, is the title of one of the two papers in 2017. However, what we tried to do was to take this logic and try to flip it around. Instead of looking for sufficient evidence for non-classicality, you might ask the question, okay, let's assume that gravity is classical in some sense. Does this bring about any particular consequences other than that it shouldn't generate an entanglement? And can these consequences, can these signatures be tested by means which are different than the entanglement tests? And what I claim and what I hope I'll convince you of is that if you assume that gravity is classical, then this must cause some diffusion in quantum matter, some Brownian-like motion in the diffusion of ordinary quantum matter. And this diffusion can be tested using non-interferometric setups. You can perform essentially semi-classical experiments on matter in semi-classical states, and you can check whether this diffusion is present or not. And in case it is absent, then you can conclude that gravity must have been non-classical, essentially falsifying unnecessary consequences the same as validating a sufficient one. So um, just as a brief outline, I'll try to condense it first using a thought experiment that diffusion should be a consequence of some very broad notion of classicality. Then I'll try to briefly formalize it mathematically, even though it's a bit of a work in progress, so it will be a bit tense, a bit, I hope, understandable in some way. Then it appears that this claim of this presence of diffusion is quantitative. Uh, we can lower bound how much the system should diffuse in order for gravity to be classical, and so we can make a quantitative claim. And then I'll briefly talk about the experimental requirements that are needed to actually perform these experiments. So to first thing first, I'll try to convince you that diffusion should be present. And to do so, I'll use a thought experiment which fixes the Feynman's original idea, that is, put macroscopic large objects which can generate a gravitational field in a superposition, but also combining it with a sort of EPR argument. So what happens if that thing was entangled with something else, possibly remotely far apart? And I'll be working under these three assumptions. That is, that matter is described by quantum mechanics, which I think is not too much objectable. I'll assume essentially the existence of a semi-classical limit. That is to say, if masses are large enough and are in essentially classical states, they're supposed to follow Newtonian trajectories. They should behave in the way we expect in our macroscopic world. And finally, I'll assume that the gravitational interaction is a classical and local. I know this is a bit vague, but I'll mostly be meaning that it cannot generate entanglement, even though I'll be touching a bit on this later on. And let's say implied by these two is also the case that we will be assuming that this channel, this classical channel, cannot be used to send signals faster than light as a sort of minimal requirement of compatibility with the special relativity. So the setup is the following: consider Alice and Bob, two faraway parties, possibly space-like separated, and they share a spin singlet space of a massive embedded in a massive particle that can generate a gravitational field. One particle of the singlet is pointed towards Alice, and they're allowed to measure the spin in any direction they so choose. And the other spin particle is pointed towards Bob. Bob has a bit of a more complicated setup. He has a Stern-Gerlach apparatus oriented along a specific axis, which is fixed and will not change. And he has a probe, as in this is, let's say, the Feynman part of the experiment. He has a probe with which he can test what is the gravitational field generated by the spin particle after it went through the Stern-Gerlach. Also, I'll be assuming that while Bob can measure the position of his probe particle, after the interaction, he can also measure the position of the spin particle. He can essentially ask whether it will upwards or downwards along the z-axis. Keep in mind, again, that the gravitation, these two particles, the spin particle and the probe will be interacting gravitationally, but the interaction will never generate entanglement between the two. This is the assumption of gravity being classical in a sense.
Yes. What do you mean by interaction? So you're thinking about local also mechanisms, or turn on and off the interaction?
The gravitational interaction. Well, I assume that after that Bob can know when the interaction between the two is relevant. Okay, so he looks at they get close. He looks at his probe. It looks what the probe does, and after a while, after he's decided that the proof has been enough, he checks what else is happening. What else has happened? So assume that Alice now measures the spin along the same direction as the axis of Bob's Stern-Gerlach apparatus. Now, since matter obeys quantum mechanics, our assumption is we have simple collapse postulate. She will measure either up or down in the z direction, and Bob's spin particle also will collapse in a state of momentum or spin, either up or down with 50-50 chance. So the state of the spin particle flying towards Bob is classical by all means. He goes through the Stern-Gerlach, it either gets reflected upwards or downwards, and then the spin particle and the probe interact. And since they are essentially in classical state, and I'm assuming they're big enough to generate appreciable gravitational fields, we expect them to behave according to Newtonian physics. So they should just attract each other. So when Bob measures the position of a probe and the position of the spin particle, he should find them always to be correlated with one another, perfectly correlated with one another. So if he sees his probe moving upwards, then he must find the spin particle that the spin particle must have been deflected upwards and correspondingly downwards with 50-50 chance. So whatever LOCC gravity is doing, it must be producing these outcomes on Bob's side. Now, the question is now, what happens if Alice instead decides to measure the spin on a direction which is different than the direction of the Stern-Gerlach, say orthogonal to it? Well, in this case, the spin particle will collapse in an eigenstate of, say she measures along Sx, then the spin particle collapses in an eigenstate of Sx, which is an equally weighted superposition of eigenstates along Z. And so the spin particle now goes into superposition of being either up or down after having traversed the Stern-Gerlach. This is the state that Feynman envisioned. Now, if you do not want Bob to guess what Alice has done, then the statistics of Bob's outcomes of where he sees that the particle must be the same in the two cases. Otherwise, you can just understand whether Alice chose to measure along Z or measure along the x-axis. But say he sees his probe moving upwards, and then he goes and tries to check what happened on the spin particle. Well, the spin particle was initially in a superposition, and if this superposition had maintained any coherence after having interacted with the probe, then there is a non-zero chance of Bob going to check and finding it, for example, that it flew downwards. So there is potentially an outcome which is different from the case in which Alice measured along the z-axis. So if you want to avoid any superluminal signaling with this classical gravitational setup, you have to assume that whatever this LOCC gravity is doing, it is causing the collapse of the wave function in space. Superposition of large objects with distinct macroscopic points must lose their coherence. And this is the first and, let's say, the most important consequence of assuming classicality. You cannot kind of escape the fact that that macroscopic objects cannot be put in superpositions, or if they can, this coherence must be lost. And in fact, finally enough, this was a consequence that was envisioned by Feynman himself in the Chapel Hill conference. Indeed, after claiming that if you put a particle in a superposition, you must believe that the gravitational field is quantized. He put forward that must be the case unless quantum mechanics breaks down on some scales. Unless in this case the linearity of quantum mechanics breaks down when you have for some amplification. That is, if these particles are too big. So this is the first important consequence. A classical gravity channel must cause the collapse of the wave function in space. Now, at this stage of this thought experiment, you might assume that there still might be a chance that this collapse of the wave function could be in a sort of way deterministic. So say when Alice measures the spin, she either sees plus or minus 1/2, and the state of the spin particle collapses into a superposition with different relative phases between the two. So you assume, oh, okay, with relative phase, let's say the relative phase is plus, then this corresponds to a specific outcome, like seeing both particles fly up. And when you have a minus, this corresponds to seeing, I don't know, both particles flew downwards. So there could be at this level, let's say, a deterministic collapse, which would still explain this, which would still be compatible with superluminal signaling. But it turns out that this cannot be the case. And the reasoning is a bit contrived. But there's a few ways of proving it, but this is the shortest one, even though it's a bit contrived. This state of the spin particle here can be seen as entangled state between the spin of the particle and the position. So if you're, let's say, spin up, you're also corresponds to being deflected upwards, and spin down being deflected downwards. However, whilst in this case they refer to the same physical system, the spin is embedded in something, and that something has this specific position. You could envision that the particle in a superposition is just entangled with the spin degree of freedom, but the spin degree of freedom is somewhere else, uh, potentially separated at space-like distances. And if that is the case, and if you can construct a bit of a contrived way to build this sort of state here. So if there was a deterministic association with the phases and what happens at Bob in a to Bob's probe, then at this external actor potentially far away, potentially space-like separates, could just flip the phase with a Z gate and change the outcome on the other side, which would open the door for superluminal signaling. So this is the, let's say, the second result of the.
It could be correlated, even though classically, without being a function. So I could have a correlated state of certain positions.
Yeah.
Without necessarily having a entangled state.
That could be the case, but I'm saying if I can build this state and there's a deterministic dependence with the relative phase of this entangled state and Bob's outcome, I can just flip the phase locally.
But if they are quantumly correlated, not entangled,
if they are quantumly correlated but not entangled, I would have to think about how do you
separable, separable, but not in a.
Yeah, what I'm thinking of is in this case, the way I'm phrasing it, let's say the determinism is that I can associate to a specific state a specific outcome. So when you say quantumly correlated, I would have to find the corresponding things I'm trying, the corresponding, how do you say? I would have to find the correspondence with certain properties of your of the state, of the correlated state to associate with the outcome. So in general, I wouldn't know how to answer at this stage. But no worries. But yeah, I would have to be more detailed. But so the conclusion is that if you want to have a classical gravity channel and you want to, under the assumption I listed before, you inevitably end up with the spontaneous collapse of with stochastic and spontaneous collapse of the wave function. And you can prove this was done by Sandor and some collaborators, so you can ask him how to prove it properly. That if you have any theory that incorporates stochastic collapse of the wave function in space, is a diffusive dynamics. Essentially, the stochastic collapse is trying to localize your system, is kicking it, trying to fix it into a specific point in space. Repeating this action stochastically essentially amounts to a Brownian motion of your system. It's a sort of inescapable conclusion of these two assumptions. So again, if you start from assuming that gravity is classical in this sense, you kind of inevitably lead to your system behaving in sort of a Brownian stochastic way. This is not a radically new idea. In fact, it is a very incomplete list of models that couple classical gravity with quantum matter in the Newtonian regime, and they all share these exact properties. The Schrödinger Newton is not listed because it doesn't respect superluminal signaling, so it doesn't count. But what's nice about this reasoning is that it kind of underlies the physical principles that underlie all of these models, which allow you to reach this conclusion. Now, all this reasoning is well and good, but it's still at the level of word thought experiments. We've been trying to formalize these ideas more properly mathematically, and it's been a bit of a hurdle, and it's still not yet complete. So I hope I'll try to be clear, but some stuff is still not completely clear to myself. And so we have to implement the assumption that I listed before, saying them in words into math. And some of them are easy to do, some of them are quite less easy to do. But we're still able to prove largely the results I showed you before. So so no signaling is the easiest to implement mathematically because it was proven in the 90s by Giselle and Kolchinsky that if you want to have a dynamic which does not violate the no signaling condition, the dynamics that is generated on the density matrix must be linear. If you have any nonlinearities, this can be used to luminary signal in a way similar that I showed you before. Then we have to implement classicality. Now, this is the asterisk I put before. Usually, what people mean by classical is an LOCC channel, so a channel that is unable to generate entanglement. And that definition comes again from the, let's say, the resource theory of entanglement. And it makes sense, it's fine. But in trying to formalize it, we adopted a slightly different definition, which has a large overlap, but it's not exactly the same with an LOCC. And it's kind of inspired by the resource theory of coherence rather than entanglement. So what we do is say, okay, what it means for before defining what is a classical interaction, you should define what are classical states. And for us, classical states are specified by choosing a privileged PVM, projective value measure. These projectors here need not be one-dimensional; they can be bigger. And we define a state to be classical if it is well supported in this over these projectors. You can think of these projectors as essentially a partitioning space in small chunks, where each chunk represents a macroscopically distinct position, essentially.
Right.
Yes.
Can you clarify with the point?
Yeah.
Linearity, you mean linearity in the normal standard sense, or linearity in like
Uncertain sense.
because if you have single system, you still have linearity because the quantum mechanical rules, right?
But we are outside basic mechanical rules because we need to. What I showed you is that there must be collapse of the wave function. So this is a very nonlinear evolution at the level of the states. But this nonlinearity at the level of state. Sorry, this might not being super clear. Like this evolution here, where you start with the superposition and you end up with the state being collapsed in one of the two cases, not happening to dynamics is not nonlinear. So it must be nonlinear. But when you take the average and you look at density matrix, it must result in a linear evolution.
And this will hold also for single systems or just like
Um,
ours.
in this, so everything here is described in a bipartite system because in absence of one of the two systems, you don't have any gravitational interaction.
But the argument for Giselle is
The argument, the necessity of linearity is also for single systems, yes.
if you take the continuous comparison localization model for that's linear, depends on the wave function itself. Okay. But what Giselle says is that if you instead of looking at the black space, look at the example, then you get it is.
Yes. Okay. So yeah, I was defining what we meant by classical, and again, given this privileged PVM, which in our minds kind of correspond to different macroscopic positions, a state is classical when it is well localized in them. Again, think of course, a Gaussian is not well localized anywhere, but well, morally is well localized in space. And what we mean by the interaction being classical is that if your parties are initially in classical state, then the output is also in a classical state. So the interaction does not generate any coherence between previously classical states. So if you have, for example, that your bipartite state, you have one system being in a generic state rho and the other prepared in a well localized state. Then the evolution essentially is local diagonal in the second system. So the second system will be localized potentially somewhere else, a different point, um, but it will still be classical. There's no, let's say, spontaneous generation of coherence dictated by this map M. And final assumption that you need to implement is the semi-classical limit, so that when objects are large and in classicalized states, they should follow classical trajectories dictated by Newton. That is to say, imagine I have this big ball here attracting this, then if from classical physics I would expect this smaller system to just be attracted, I translate this into in quantum mechanics by saying that this happens almost surely, so that the states remain classical and they almost surely follow classical trajectories. So in terms of the block diagonal decomposition of the map M, you can translate this into a statement on the probability of having certain outcomes uh, when you measure your systems. And with this assumption here, so again, just a final comment on the block diagonality. Again, if one of your system is already in a classical state, then you can write the evolution as a sum over um, the index of the potential outcome, let's say the potential points where the system that is still classical might be. And in each case, you apply this J tilde, which is essentially saying if I find my system at position y after it was at y0, I must apply this CP map um, on the system. And in using these three assumptions, you can actually prove the two things I told you before with the thought experiment. That is, the map must be um, cannot be unitary. There must be some irreversibility or stochasticity, as I used before, and that there must be collapse of the wave function. The absence of the map cannot satisfy all these properties, and unitary is almost trivial. Uh, the point is the map must correlate with states who have an interaction. This is what is happening here in these probabilities. Essentially, classical states are getting correlated because of the interaction. But a unitary map also preserves purity. So what happens is that if you start with a superposition of pure states interacting with a pure probe, and the map is unitary, you end up with a system which is essentially entangled as long as the system here is attracted enough that it goes into states that belong to different sectors, that belong to different projectors, so to different macroscopic positions. So essentially, if you have this, if you want to have any interaction at all, and you want to have a solution, you end up inevitably failing at the evolution being classical according to this definition. Now, showing that there is collapse is complicated. It's not complex. It's just a knowing calculation of this probability over this probability here. But you can essentially show that what is the support of this J tilde. So recall before we had a superposition of two positions interacting with a probe, and you ended up in either of these two states. And you can show indeed that the support of this J tilde, which are what happens to the system if I find the probe, so the system that was in a classical state at position yx, you can show that it has support exactly on the projectors corresponding to Newtonian trajectories. So if I have this particle being attracted, if I have this probe attracted downwards, I see that the J tilde corresponding to this event can support exactly on the state being collapses. So essentially, the state condition on where I see my particle or where I see my probe has support essentially on a single projector. And so any coherence that I had in my initial state must have been killed in the process. Okay. So this is, let's say, the formalization that we came up with is still a bit incomplete, but we're able to kind of formalize the main features that were shown in the thought experiment. But now I want to go towards the characterization and a more quantitative claim in an experiment of what this diffusion should look like. And what we envision as a sort of experiment, and diffusion is a non-interferometric signature that happens in in principle in any state that you want. So you're not limited to using small microscopic quantum systems. And so we envision a sort of setup where you use very massive, large system. You can think of like 2 kilogram torsion pendulum interacting with one another, and you monitor their position close enough to check whether they deviate from their standard oscillation that you would expect. Now we need to model the diffusion, so the action of the gravitational, of the classical gravitational channel. And within this experimental setup, where we assume that the system are very well localized, we assume that we can make a few approximations. The first is that we can describe it instead of with a map, but um, with a Markovian GKSL evolution. And we also assume that we're working within a regime in which we can make a Gaussian approximation. So we can write down the most general GKSL master equation, which incorporates all the assumptions that we listed. So linearity of the evolution needed for compatibility with the relativity. Well, complete positivity is also assumed for consistency. And you must have a first Hamiltonian evolution with the presence of the Newtonian interaction. This makes it so that macroscopic objects in well-localized states follow Newtonian trajectories, and we need to add the Lindbladian. This is just a generic Lindbladian with the Kosakowski matrix gamma, which encodes the gravitationally induced diffusion. And the last thing that we need to impose is that the systems do not, these two systems in their evolution do not get entangled. We want to require that the diffusion is such that the system will not become entangled. And this actually gives a quantitative bound on the gamma matrix we can prove using the positivity under partial transposition, which is the one that you find here. So the sum, essentially, of the local coefficients which are governing the diffusions in position and momenta of these two systems must be greater than the entangling potential in order for this, in order for the dynamics to not generate entanglement. So just to recap the flow of the logic, we showed that if gravity were classical, then it must induce, it must cause the collapse of the wave function, a stochastic collapse of the wave function of matter in space. That this must cause some diffusion, which we codify in this experimental setup in this gamma matrix, and these gamma matrix are lower bounded by the strength of the gravitational Newtonian coupling in order for the system to be separable. So if you actually monitor the evolution of these oscillators, and you can show that this bound is violated, then you're falsifying a necessary consequence of our assumptions of classicality, and thus you would be able to conclude that gravity ought to be described by a non-classical channel in some form. Now, we studied a couple of experimental setups which could be used to test this effect. Yes? Yeah. No, gamma is general. We have a constraint just on the diagonal. Yes. But I'll show you in the next slide where this pops up. So we have a couple of, we have considered two sort of experimental detection strategies of this experiment. One is to just have these two oscillators being prepared in a very cool state, like possibly the ground state, and then let them evolve in the dark and check for a full heating rate and see how it compares with the bound I showed you before. Or you can you can continuously monitor the evolution of this oscillator and look at the spectrum. And in this case, I have plotted here the formula of the spectrum that you calculate in the presence of this diffusion, and you have these diagonal entries showing up here, which corresponds to a heightening of which change of the spectrum. You do have contributions of, like most of the contributions drop out, which is kind of nice, and the few contributions which are left, which could kind of in influence this claim are all um, suppressed by the damping, by the quality factor essentially. And since these experiments to be performed would require extremely high quality factor, as I'll tell you in a second, these are can be largely ignored. So essentially, if you perform these experiments and you see that this, and you can characterize them different, that these contributions are less than this bound, then again, you can conclude that the mediator of the interaction must have been non-classical. Now, you can, now this is all nice. And again, this is a nice experiment in the sense that it doesn't require particularly, it doesn't require general superposition. It's essentially a classical experiment. You're just monitoring the positions of a classical object very closely, but you need to do so very, very accurately. And the accuracy needed is staggering. You can quantify it with a ratio of the quality factor of your oscillator to temperature, and it is 10 to the requirements are 10 to the 14. So even if you're able to, I don't know, take two millihertz torsion pendula of like kilogram masses and cool them down to millikelvin, you would still need a quality factor of 10 to the 11, which is like 4 or 5 orders of magnitude away from the best torsion pendula experiments that I'm aware of. So these experiments are still like very far away from very challenging to perform. But I think anyways, I hope I showed you that there is it's interesting to look at, there's still a lot of interesting avenues that can be explored within this realm. Many more experiments will come up. I think this experiment does bypass some of the hurdles of the gravitational-induced entanglement experiment. It fights with some different, it has different kind of problems, but it is useful to tackle the problem, let's say, from different perspectives, from different avenues. So, okay, I hope this was interesting. And if you have any questions, I'm here to answer.
Questions?
Mm-hmm. Yes, this is the platform. Yeah, yeah. This is yeah. This can be written in, but you just need to rearrange a bit. But yes, this is positive semi-definite.
So if there is no more curiosity, anything more? Good. Okay, so we have Oliviero.
Thank you.
So should anything come up? Find them in my